whispering to you this book titled, What Are the 7 Wonders of the Modern World? So this is a neat little series. I actually checked out the ancient world version, but the books are too long to read all in one video. So there's the ancient world and the natural world, and just in the United States. So these are all man-made places around the world that are modern wonders. And I thought we pull out my little handy dandy map so I can point out to you exactly where they are and draw on the map, because I really like this. I hope you guys do too. Also, this is part of my Viewer's Choice series. This was requested by Big Lad. Thank you for choosing it. Great topic. Alright, so in this book, The 7 Wonders of the World, the first one is in my home area, my old stomping ground of San Francisco. It is the, make sure the glare's not, okay, the Golden Gate Bridge. You know why the glare's not there? Because I forgot to turn on my filming light. Hold on. There we go. Much better. The next one is in New York. It is the Empire, you can see, Empire State Building. The next one is down here on the Parana River, Brazil and Paraguay. It is the Itaipu Dam. Then over here in Europe, it's going to be hard to draw because they're close together. Right here is the Channel Tunnel, or the Chunnel. And then up here is the, oh, what are they called? What are they called? Hold on. I wonder if it says on the back. No. It's the dams in the Netherlands, but I forget their formal name. This North Sea Protection Works. North Sea Protection Works. Then, let's see, that's 1, 2, 3, 4, 5. Down here in the United Arab Emirates, right here in Dubai, is the Burj Khalifa. The Burj Khalifa. Do I remember the last one? Do I remember it? Let me look. Oh yeah. Over here in Panama, right, like here-ish, I guess, is the Panama Canal. So, according to this book, these are the 7 wonders of the modern world. You might disagree. And some of these facts, especially about the Itaipu Dam, are going to be a bit outdated because this book came out about 15 years ago. But still not a bad list, I think. Pretty interesting. So let's get, oh wait, let me erase first. I've been to 2 of them. Obviously, I've seen the Golden Gate Bridge more times than I can list because I used to live there. Personally, I don't think it's a really impressive bridge, but when I read the book, I was like, you know, it is pretty neat. I like the Bay Bridge better. And I've been through the Channel Tunnel when I visited Paris when I was visiting England. But it was not a great experience. It had construction work, and we were stuck in the tunnel under the water for 4 hours, you guys. It was aggravating. I was just eating cheese sandwiches and just staring out at the dark of the tunnel for hours, and then we were super late to check into our hotel. It was a whole thing. But let's read the book. The 7 Wonders of the Modern World. Let's start by reading Chapter 1, Humans Against Nature. Each of the structures in this book began as a dream to move faster, go higher, or live better. The Panama Canal, for example, was built to speed travel between the Pacific and Atlantic Oceans. Its construction required removing enough dirt and rubble to open a 16-foot wide or 5-meter tunnel to the center of the Earth. The Channel Tunnel, an undersea train tunnel that stretches from Britain to France, was also built to help people travel faster. The need for speed was considered in all aspects of this project, God's rain. This video is a mess already. Anyway, the trains that move through the tunnel have a locomotive on each end to hasten a train's exit in case of emergency. Some structures were built to go higher than ever before. The Empire State Building, for instance, was built to fulfill a dream to construct the highest building in the world. It is so tall there's over 17 million feet, or 5 million meters of telephone wire inside it. This is more than enough wire to stretch from New York City to Los Angeles, California. The nearly 2,717 foot tall, or 828 meters Burj Khalifa, was also built to go as high as possible. The building has returned the location of Earth's tallest freestanding structure to the Middle East, where the Great Pyramid of Giza claimed this achievement for almost 4 millennia. There's a little map. The desire to live better is what motivated the construction of the North Sea Protection Works. These dams and barriers hold back the ocean and protect the people of the Netherlands from flooding. Its longest dam is the Oosterschelde Dam, which, let me know, Dutch viewers, I know you're out there, hello. If I grossly mispronounce anything, just go ahead and correct me down in the comments, okay? I appreciate it. Dutch is complicated. It is as long as 1,000 school buses parked end to end. Itaipu Dam in South America began as a vision to create electricity for the people of Paraguay and Brazil. The completed energy plant includes a dam so massive it contains enough iron and steel to build 300 Eiffel Towers. None of the structures in this book were easy to build. Each one pitted human ingenuity and perseverance against nature. In the end, human desire triumphed. Along the way, new machines were often invented and new engineering methods devised. For example, the engineers of the Golden Gate Bridge worked for months solving mathematical equations to create a bridge that could withstand 100 mile per hour or 185.2 kilometer per hour winds. Their work was done before the age of computers, with nothing more than slide rulers and adding machines to crunch numbers. The result, a bridge that safely swings usually 28 feet or 9 meters. As their creators imaginatively overcame obstacles, these structures became the marvels of their day. The 7 wonders of the modern world are examples of modern society's ability to achieve the impossible. Chapter 2, the Panama Canal. The Panama Canal creates one of the longest shortcuts in the world. Before it was built, ships going from the Atlantic Ocean to the Pacific Ocean had to sail around South America. The new canal made it possible to cut through Panama, a country at the southern end of North America. This took about 8,000 miles or 13,000 kilometers off the journey. It is such a useful route that thousands of cargo, military, and cruise ships travel through the canal each year. The need for a canal. People have dreamed of connecting the oceans as far back as the 1500s. It would be centuries, though, before the proper machinery and know-how made a canal possible. In the late 1800s, a canal seemed achievable. The French were the first to try. However, their machines were too small, and tropical diseases killed many workers. By the end of the century, they had given up. The dream did not die, though. United States President Theodore Roosevelt saw how valuable a canal would be for moving goods and people. Furthermore, he was convinced a canal was essential to the defense of the United States. It would allow the American Navy's fleet of ships to move quickly from one side of the country to the other. In 1903, the United States government paid Panama $10 million for the right to build and operate a canal there. The first task was to make the area safe for workers. Crews cleared brush and drained swamps, killing millions of disease-carrying mosquitoes that had devastated the French attempt. A cut, a lake, and some locks. Soon, steam shovels were digging through the hills on the Pacific side of Panama. The earth here was very loose, and landslides slowed the work. It took several years to make a cut 8 miles or 13 kilometers long. During that time, tons of earth were removed to make a channel called the Gallard Cut. The earth taken from the Gallard Cut was hauled by train to the other side of the country. There it was used to make a dam across the Chagres River. Once finished, the dam packed water into a valley to create Gatun Lake. Gatun Lake and the Gallard Cut would form the main waters of the Panama Canal, yet both lay above ocean waters. Therefore, ships ships between two levels of water. A vessel moves into a lock, and the gates of the lock are closed. Water is poured into the chamber or drained out until the level inside the lock is the same as on the other side of the water that the ship is moving toward. Then the gate opens and the ship sails out. Like in the picture here, you can see the ship's in a lock, and they're going to drain the water out of this lock, so it's going to lower until it's in this level, and then it can sail on. Pretty cool idea, I think. That's pretty genius. The locks of the Panama Canal were one of the biggest engineering challenges of the project. They were built in pairs to allow vessels to travel both ways on the canal at the same time. At 110 feet or 34 meters wide and 1,000 feet or 305 meters long, they were the largest concrete structures ever built. The steel gates for the locks were also massive. Each one weighed more than 700 tons, or 635 metric tons. They were opened and closed with a 40 horsepower engine. This is the same motor used to power a small boat. The cost of a canal. During the busiest construction period, almost 45,000 people were working on the canal. Most came from the British West Indies, but many were from the United States. The canal was completed in 1914 at a cost of $352 million. Another kind of cost was the number of deaths. Over 5,000 people died from injury or illness while working to complete the canal. Through the canal. On August 15, 1914, the first ship, the SS Ancon, sailed through the Panama Canal. Its journey was much the same as the trip is today. A vessel coming from the Atlantic Ocean is hooked to locomotives that guide it through the Gatun locks. These locks raise the ship 85 feet or 26 meters to Gatun Lake. After a 32-mile or 51-kilometer journey across the lake, the ship sails through the Gallard Cut. At the end of the cut, it enters the Pedro Miguel locks. These lower the ship to 30 feet or 9 meters to another lake. From here, it moves through the Miraflores locks and is let down another 52 feet or 16 meters to the Pacific Ocean. The 50-mile or 80-kilometer trip takes about 8 hours. The locks by the Pacific Ocean lower ships 3 feet more than the Atlantic Ocean locks. This is because the sea level here is 3 feet lower. The canal today. In 1977, the United States agreed to gradually transfer ownership of the canal to Panama. The transition was complete at the end of 1999. Since then, Panama has improved the canal by widening the Gallard Cut and improving the locks. With these changes, the hope is that the canal will be used for many years to come. Chapter 3, the North Sea Protection Works. And again, if I grossly mispronounce any Dutch, let me know. People who live in the Netherlands are fond of saying, God created the world, but the Dutch created Holland. The Netherlands, sometimes called Holland, which is not true. Part of the Netherlands is called Holland, is a country in Europe that borders the North Sea. Its people are known as the Dutch. Much of the Netherlands lies below sea level, making it easy to flood. For centuries, the Dutch built dikes to hold back the sea. Sometimes they built dikes around shallow water, then emptied the area using windmill-powered pumps. The water was channeled back to the ocean through man-made canals. The newly drained land, called a polder, was used to live on. Farms, towns, and even large cities have been built on polders. Yet dikes have not always held back the sea during severe storms. When a dike broke, water often washed away houses, farms, and people. Two devastating storms, one that occurred in 1916 and another in 1953, prompted the Dutch government to build new barriers along the sea. The resulting dams and floodgates are known as the North Sea Protection Works. Alright, I think it's the Zuiderzee Works. I think. In 1916, a terrible storm killed hundreds of people around the Zuiderzee, a large inlet on the northern part of the Netherlands. The government immediately planned a protection project called the Zuiderzee Works. First, a 19-mile long or 31-kilometer dam was built across the Zuiderzee. The structure was made from clay, sand, stone, and mattresses of small trees and bushes. This dam was 25 feet or 8 meters high and as thick as a football field. Some of the water inside the dam was drained, creating an area of boulders that was called Flavoland. The remaining water became a freshwater lake named Iselmere. This part of the North Sea Protection Works was finished in 1932. Hold on, I have to itch my shoulder. Oh my gosh, it's like driving me crazy. Oh my gosh, it's at a spot I can't reach. There we go. Okay. Anyway, moving on. Usually I cut those things out, but we're just going for it today. When another huge storm blew across the North Sea in 1953, the Zuiderzee Works held. However, nearly 2,000 people in the southwestern province of Zeeland were killed by flooding waters. Determined to prevent another similar disaster, the Dutch government began a program called the Delta Plan. The Delta Plan sounds mysterious and ominous, doesn't it? Zeeland is a land of peninsulas and islands interrupted by several deltas. A delta is a fan-shaped deposit of sand and soil that forms at the mouth of a river. Engineers decided that the region needed several different kinds of barriers, so they planned various structures, not sure of how the larger ones would be built. But they felt confident that as the smaller structures were constructed, the technology and expertise for making the bigger pieces would develop. First, several dikes were heightened. Then 3 main dams were built across the estuaries of the Rhine, Maas, and Scheldt rivers. An estuary is the place where a river meets the sea. Channels were left open for ocean vessels to get to and from Rotterdam, the Netherlands, and Antwerp, Belgium. Then it was time to build the most complex part of the project, a surge barrier that would dam the Oosterschelde estuary. And I believe this is the Oosterschelde Dam. The Oosterschelde Dam was planned as a closed barrier. However, fishermen and conservationists knew this would destroy much of the marine life inside the dam. They persuaded the government to build a barrier that would remain open most of the time, but be closed when bad weather threatened. This would minimize interference with the natural environment. 65 giant concrete piers were needed, each weighing around 18,000 tons or 16,000 metric tons, and standing as tall as a 12-story building. 2 artificial islands were built in the Oosterschelde estuary for constructing the piers. Once the piers were completed, specially made vessels towed them into the sea and struck them between the work islands and the mainland. Computers aboard the boats and on the shore guided the positioning of each. The technology was so precise, every one of the piers was placed within 4 inches or 10 centimeters of its planned position. Then tons of sand and rock were piled along the bottom of the piers, anchoring them against the battering tides of the North Sea. Next, huge steel gates were lowered between the piers. These gates could be closed by a control station on one of the work islands. The gates and mechanisms were so well engineered, the entire barrier can be closed in just 1 hour. The Oosterschelde storm surge barrier was finished in 1986. My goodness, I need to clear my throat. Okay, I did cut that out. That was too loud. Living with the sea. The final price tag of the Delta Plan alone was $5 billion. That's US. To the Dutch, the safety is well worth the money. In addition to providing safety to the people of Holland, the dams have created new recreation areas. Roadways have been built on top of some to improve transportation routes throughout the region. Finally, the larger dams are a tourist attraction. A museum near the Oosterschelde Dam describes how the dams were built. The North Sea Protection Works has been called a wonder of the world because of its size and the technical expertise needed to create it. One professional magazine remarked, "It is unique, expensive, and quite unlike any other civil engineering project to be found on this planet. It is proof that even if the Dutch did not actually create Holland, they are certainly preserving it." Chapter 4 is the Empire State Building. The movie audience gasped. What would King Kong do with the beautiful heroine Fay Ray when he got to the top of the skyscraper? Everyone watching the 1933 movie knew the gigantic ape was climbing the tallest building in the world, the Empire State Building. It was was and still is one of the most famous structures ever built. The Empire State Building is located in New York City, and it was the world's tallest building from 1931 until 1972. Today, only a handful of buildings rise higher. I suppose. The race to the sky. During the late 1800s, builders began using steel to frame tall buildings. Steel frameworks made it possible to erect taller and taller structures. Soon the skyscraper was born, and each one seemed to go higher. Before long, some people made a competition of erecting the world's tallest building. First came the Woolworth Building in 1913. It is 792 feet, or 241 meters high. The Bank of Manhattan Trust, now known as the Trump Building, topped this in 1930 at 927 feet, or 283 meters. The Chrysler Building was next, also in 1930. It is 1,046 feet, or 319 meters tall. Yet, even before the Chrysler Building was finished, investor John Jacob Raskob was making plans to go higher. He wanted to erect a building as a tribute to America's wealth of opportunity. Raskob named his dream after New York State nickname, and the Empire State Building began taking shape. Designing the building. New York City zoning law said that tall buildings could not block sunlight from reaching the street, so the 1,250-foot or 381-meter building was designed to decrease in size as it grew taller, allowing sunshine to fall to the ground. Mail chutes, bathrooms, and elevator shafts would be built in the center of each floor, with office space around the outside. This would allow every worker to be within 25 feet or 8 meters of a window. The building also had to include enough elevators to move thousands of people among 100 floors. The finished structure would boast 73 elevators. Finally, Raskob wanted the top of his building to have a docking station for dirigibles. At the time, these airships were used for transportation. Building the world's tallest structure. By March 1930, the building site had been cleared, and the footings, or the parts of the base that make sure the building is not tilted to one side, were set. Then, like giant pieces from an erector toy construction set, exactly measured beams and girders were delivered for the building's frame. These beams and girders already had rivet holes drilled into them. As steel workers framed the building, other workers followed behind, pouring concrete for each story's floor. Next came more workers who installed the limestone blocks and windows of the exterior walls. Behind them, electricians, plumbers, and carpenters finished the interior spaces. At the height of construction, more than 3,000 people were working on the building at once. In order to keep all of these workers busy, an immense amount of supplies had to be at the right place at the right time. A company was hired for the sole purpose of organizing and delivering materials. This assembly line method was new to the construction industry. It was also fast. It took only 7 months for workers to get to the 86th floor. Other builders noted this efficiency and were soon utilizing the same procedures. Obstructions. There were some problems with the construction of the Empire State Building. One was the wind. The higher in the air, the stronger the wind's force. So engineers designed special ways of connecting the framework to improve the building's strength against the wind. These and other techniques made the building so solid it was easily repaired when an airplane accidentally crashed into it in 1945. Even so, strong winds can still cause the building to sway. The wind also caused problems with the dirigible dock. A 200-foot or 61-meter tower on top of the 86th floor was meant to be the mooring mast for dirigibles that would help the airships dock. 2 airships tested the dock, and both could barely land due to high winds, so the plane was abandoned, and an observation deck was installed at the top of the tower instead. This was the equivalent of the 102nd story. The worst setbacks of all were the accidents. 5 people were killed during construction. The emphasis on constructing the building quickly may have been the cause. Yet this did not slow the pace for long. The Empire State Building was finished 14 months after site excavation began. The grand structure alone had cost $24,718,000 US to build. The entire project cost about $40.9 million. pressed a symbolic button in the White House to turn on the lights. Today, the building is filled with over 10,000 places of business, ranging from banks and offices to restaurants and jewelry stores. However, there are no offices in the building's tower for safety reasons. In addition, millions of tourists visit the 86th floor observation deck each year. The 102nd floor tower observation deck has been closed to the public because officials determined it was not safe. Raskop succeeded in building a tribute to his beloved country. The result was so spectacular, in fact, that even though the Empire State Building is no longer the tallest building in the world, it has become a symbol of America known around the globe. It's not even the tallest tower in America anymore. That's One World Trade Center, also in Manhattan. But moving on to Chapter 5, the Golden Gate Bridge. Few people visit San Francisco, California without seeing the Golden Gate Bridge. This splendid, bright orange structure spans the entrance to San Francisco Bay, connecting the city to Northern California. The Golden Gate Bridge is 8,981 feet, or 2,737 meters long. It was the longest suspension bridge in the world for 27 years after it was completed in 1937. You know, a cool fact that only San Franciscans know, is the tunnel in the North Bay. When you leave San Francisco, or I guess when you're heading into San Francisco, you drive through what's now called the Robin Williams Tunnel, and it's painted a big, beautiful rainbow. It's great. Yeah, we after his passing, it was named the Robin Williams Tunnel. But moving on, we need a bridge. San Francisco sits at the end of a peninsula separated from Northern California by the Golden Gate Strait. A strait is a narrow body of water that joins two larger bodies of water. For many years, the only way to cross the strait was by ferry. During the 1920s, the ferries became more and more crowded, and people often waited for hours and even days to cross. A bridge seemed like a logical solution, and a group began raising money for the project. Other people thought the idea was foolish. They believed that the constant fog, high winds, earthquake problems, and strong ocean currents made a bridge impossible. They called it the bridge that couldn't be built. Oops, spoilers. What's next? Strauss's certainty. Engineer Joseph Behrman Strauss disagreed. He designed a suspension bridge he felt could withstand all of these natural forces. His bridge would consist of two towers strung with thick metal cables that held up a 6-lane road. It would need the tallest towers, the largest piers, and the longest and thickest cables ever built. Strauss was confident it could be done. Work on the bridge begins. Work on the bridge began in January 1933, when enormous concrete blocks were laid on either side of the strait and fastened to bedrock. The bridge's cables would be attached to beams and cemented into the blocks. These anchors would keep the weight of the bridge from bending the towers toward each other. Meanwhile, concrete piers were being built to hold each tower. Strauss and other engineers designed the bridge so the two towers could be as close together as possible while still creating the needed span of 4,200 feet, or 1,280 meters. Therefore, the position of each pier was determined by engineering considerations rather than by the convenience of any particular site. This created problems. The northern pier was situated in shallow water, and it went up easily, but the southern pier had to be built in deep ocean water. A special kind of dam had to be built before the pier could be constructed. This held ocean waters back so the workers could complete construction of the pier. The San Francisco pier was finally finished in late 1935. The towers. Now the towers could be erected on the top of each pier. A crane hoisted land-built sections into place. Then workers fastened them together. The finished tower stood 746 feet, or 227 meters tall. Suspension cables were then strung from the anchor on one side of the bridge over the towers and into the anchor on the other side. Each one was about 36 inches or 91 centimeters in diameter. The two cables contained 80,000 miles or 128,720 kilometers of steel wire, enough to circle the Earth 3 times. The exact sag of the cables was carefully calculated. The cables had to be tight enough to support the road below also had to be loose enough to allow the bridge to move due to stress or temperature changes. This flexibility would keep the structure from cracking during earthquakes, storms, or extreme weather changes. Next, the cables for the road were hung from the suspension cables. They were each positioned to make the road 220 feet or 67 meters above the water so that United States Navy ships could pass under the bridge. Building the road. The road, which is US Highway 101, was built in sections starting at each of the towers and moving out in both directions at the same pace. This kept the strain on the towers and cables even. Sadly, 10 men were killed while building the road. This brought the total number of deaths during the bridge's construction to 11. Finally, it was time to pave the roadway deck and paint the bridge its unique international orange color. The bridge was finished in 1937, 4 years after it was begun. It had cost a total of $27 million. Success. On May 27, 1937, 200,000 people celebrated the opening of the Golden Gate Bridge by walking across it. The next day, an official dedication ceremony was held, and the day after that, the bridge was opened to traffic. Since then, the bridge that couldn't be built had been used by millions of people. It has been closed due to bad weather only 3 times, and it survived a large earthquake in 1989. True, the Bay Bridge did not survive it, but the Golden Gate did. Today, engineers are working to make it even more earthquake-proof, ensuring that the Golden Gate Bridge will remain a San Francisco icon for years to come. Chapter 6 is about the Burj Khalifa. It's not hard to pick out Burj Khalifa. It is the building that soars above Dubai's highest skyscrapers, making them look like toys beneath it. Yet, Burj Khalifa is not just the tallest building in Dubai. At 2,717 feet, or 828 meters, Burj Khalifa is the tallest building in the world. Dubai is a city in an emirate also named Dubai. An emirate is like a state or a province. Dubai Emirate is part of the United Arab Emirates, a small country on the Persian Gulf. The city of Dubai grew quickly during the 1990s to become a financial center and popular tourist destination. It soon became known for its over-the-top structures. This desert city boasts an indoor ski hill and a luxurious hotel built to resemble a sail. It is also home to a housing development of man-made islands shaped like a map of the world. Therefore, it was no surprise when ground was broken there in 2004 to build the tallest building on the globe. Burj Khalifa opened in 2010. The 160-story skyscraper, topped with a 700-foot or 213-meter steel spire, is more than 1,000 feet or 305 meters higher than the previous record holder, the Taipei 101 in Taiwan. A flower made of steel. The Hymenocallis, a flower with spiraling petals, inspired Burj Khalifa's design. 3 wings in the shape of a Y extend from a central core. These wings rise skyward in large sections. Each section is set back from the one below it, and the sections on each wing vary in height. The staggering creates a spiraling effect. The spiraling design increases the number of views from the building to the Persian Gulf. It also allows lots of sunlight into the building. A facade of aluminum, stainless steel, and glass make the building shimmer in the desert sun. A vertical city. Burj Khalifa can hold 35,000 people. It is sometimes called a vertical city because it contains many of the things found in a normal city. There are apartments, business offices, hotel rooms, fitness centers, restaurants, grocery markets, a daycare, and even a mall. The highest swimming pool in the world is on the 123rd floor. The highest house of worship is the mosque on the 158th floor. Cool facts. A number of floors are dedicated to making the building run. Some are electrical substations, others are filled with water tanks and pumps. A few floors are devoted to communication equipment for broadcasting. Burj Khalifa's 124th floor is an observation area. Its walls are made of glass. The area has a terrace for outdoor viewing, making it one of the world's highest outdoor observation decks. On a clear day, it's possible to see 60 miles or 97 kilometers into the distance and across the Persian Gulf to Iran. tallest skyscraper presented several design challenges. First of all, the building needed to be safe in the case of a fire, so engineers had all of the stairwells surrounded in concrete. Another challenge was figuring out how to move people up and down inside the building. Because an elevator is not able to travel 160 stories, there had to be a system of elevators that would work like vertical roads. Some elevators function as shuttles. They travel several stories before stopping to let people unload, and board elevators that move floor by floor. One of the biggest design challenges was the wind. Winds at high elevations are powerful, so engineers must find ways to make tall buildings especially sturdy. The designers of Burj Khalifa used a wind tunnel to test their ideas. They found that their Y-shaped base and staggered levels would help the soaring skyscraper withstand the wind. Engineers also made the building slightly flexible so it could sway in the wind rather than break. This sway is so small it cannot be felt. Going up. Construction on Burj Khalifa began in January 2004 with the sinking of almost 200 column-shaped foundations known as pilings. Each piling was buried more than 164 feet or 50 meters deep to create a sturdy anchor. It took more than 4 years for workers to build up to and complete the 160th floor. Next came the erection of the spire. Finally, the outside of Burj Khalifa was clad. As finishing touches were put on the building, the landscaping around it was also completed. Acres of park filled with flowers, trees, pools, and water fountains surround the building. People power. It took about 12,000 people to build Burj Khalifa. Among them were engineers, architects, electricians, plumbers, drafters, interior decorators, mechanics, carpenters, and thousands of construction workers. Many of the construction workers were immigrants from South Asia who were not always treated well. In a place where the average monthly income was around $2,000, these workers earned under $200 a month. Many lived in labor camps where they shared a small room with several other laborers. Furthermore, the workers were often exposed to dangerous situations. In spite of these poor working conditions, Burj Khalifa was completed in late 2009. On January 4th, 2010, Dubai officials held a huge ceremony to celebrate its opening. Fireworks and a dazzling light show lit up the sky, while the water fountains around the skyscraper were programmed to dance to traditional and modern music. Wave of the future started raining again. Wave of the future. It cost about $1.5 billion to build Burj Khalifa. Many people have criticized the use of so much money and resources to build the skyscraper. They believe it was nothing more than an opportunity for Dubai to boast about another spectacular building. Others have said that tall buildings are the wave of the future. Indeed, there are already plans underway in other countries to build even taller skyscrapers. Yet, no matter how they feel about the Burj Khalifa itself, few people would deny it is an incredible engineering feat. Chapter 7 is the Itaipu Dam. It is hard to imagine a hydroelectric dam large enough to supply all the electric power needed to energize an entire country. Yet that is exactly what Itaipu Dam does. Located in South America between Brazil and Paraguay, the Itaipu Dam supplies nearly all of Paraguay's electricity and about 1/4 of Brazil's. It is in fact the largest renewable power plant in the world. Okay, I double checked this because I was like, surely Three Gorges is bigger than Itaipu. It says Three Gorges wasn't finished when this book came out. And I googled, and yes, Three Gorges is technically larger, but I also read that the power that it generates is about equivalent to Itaipu, so you can debate that, what's the largest dam in the world. But China last year opened a solar power farm that's bigger than Itaipu, so that is now the largest renewable power plant, technically. But yeah, at the time of this book came out, that was a correct fact. A cooperative effort. In 1973, Brazil and Paraguay decided to work together to build a hydroelectric dam on the Paraná River. The Paraná, the 7th largest river in the world, runs for several miles along the border that these two countries share. The dam site was chosen at a place called Itaipu. In 1975, earth-moving machines were used to dig a channel that would change the course of the river. This exposed the riverbed so the dam could be constructed. Diverting the river involved moving millions of tons of earth and rock, and it took almost 3 years. Once the space was ready, 5 different dams were built. The main dam was in the center. It was as high as a 65-story building. Two buttress dams were built on either side of it, and each of these was flanked by an embankment dam. Together, the structures were about 5 miles, or 8 kilometers long. When the 5 dams were completed in October 1982, the diversion channel was blocked, and water began rising behind the dam. Then crews went out in boats to collect animals endangered by the rising water. Eventually, the released river created a reservoir over 14,000 square miles, or 36,260 square kilometers in size. This is larger than the combined size of Massachusetts and Connecticut. The powerhouse. In an effort to stop water from the Panama from flowing over the dam, 18 enormous concrete pipes called penstocks were lined up vertically against the 5-mile or 8-kilometer dam. At the bottom of each penstock was a turbine and a generator. These 18 generators formed the powerhouse that would create the electricity. Each penstock would channel water from the reservoir in the powerhouse. The flowing water would spin the turbines, driving the generators to create electricity. The first generators were ready to begin work in May 1984. 2 or 3 more went into operation each year after that. By March 1991, the last generator was up and running. Delivering electricity. As the dam and powerhouse were being built, a system of transmission lines was constructed from Itaipu to cities in Paraguay and Brazil. These would create a power grid to carry the electricity from the plant to the people. The many components of the dam called for a massive labor force. At the height of construction, 30,000 people were working on the project. The total cost of Itaipu was $18 billion. Itaipu's success. The Itaipu Dam has been an overwhelming success. Its energy production has broken records, and in 2000, the dam produced a record 93.4 million megawatt hours of energy. This is enough to supply all of California. Plus, Itaipu emits no pollutants. Itaipu was an immense engineering feat. It is said that if the technical drawings for the project were stacked up, they would rise to the height of a 50-story building. Perhaps even more significant, though, is Itaipu's testament to how cooperation between nations can benefit all. And lastly, Chapter 8 is the Channel Tunnel. Traveling in a train under the floor of the sea seems like something from a science fiction movie, yet the Channel Tunnel is a reality. It connects France to England and is often referred to as the Chunnel. An easier way to travel. Britain is separated from Europe's mainland by a strip of water called the English Channel. For centuries, the only way to cross the channel was by boat or airplane. Both were time-consuming and often uncomfortable. Several solutions had been proposed over the years, including a tunnel, a bridge, and a combination of both. But the expertise for any project was not available until the 1980s. Then, engineers believed a tunnel through the soft rock at the bottom of the channel was possible. Designing the Channel Tunnel. Knowing that an automobile tunnel would present too many ventilation problems, engineers proposed a tunnel for trains that could carry motor vehicles. These trains would be 14 feet or 4 meters across, the widest ever built. The resulting design was of 3 tunnels that ran parallel to each other. One was for trains going from Britain to France, and another for trains moving from France to Britain. The third tunnel was for maintenance and emergency vehicles. It would run between the 2. Sonar and borings helped engineers determine the best route for the tunnel. It would cross the channel at one of its narrowest places, the Strait of Dover. The tunnel would begin at Folkestone, England. There it would dive underground for 32 miles, or 51.5 kilometers, to emerge at Coquelles, France. 23 miles, or 37 kilometers, of the tunnel would run 150 feet, or 46 meters, under the bed of the sea. Tunneling through the earth. 1997 when shafts were dug into the earth on each side of the channel. Then specially designed tunnel boring machines, or TBMs, were lowered. Sorry, my eyes are blurring. I'm getting sleepy. Were lowered into the shafts. Each TBM was as long as 2 football fields. Their cutting heads were 30 feet or 9 meters in diameter. As each machine cut its way through rock, one driver and a computerized laser guidance system kept it on course. The resulting debris was moved out by a conveyor belt, then taken back to the appropriate shaft. On the British side of the channel, the material was dumped into an artificial lagoon created by a huge seawall. The water eventually evaporated, and a new piece of England was created. On the French side of the channel, the debris was dumped into a lake near the coast. Once filled, it was planted with grass. As each TBM moved forward, machinery at the back lined the tunnel walls with pieces of pre-shaped concrete. These were later reinforced to make each tunnel wall 5 feet or 2 meters thick. When the tunnels were 300 feet or 91 meters apart, the TBMs were stopped. The remaining distance between the tunnels would be drilled with smaller machines so that the 2 ends could be perfectly aligned. Then the 2 tunnels would become one. The TBMs had no reserve gear, and they could not be backed out of the tunnels, so when their job was finished, the machines on the English side were aimed downward, and each burrowed itself into the bottom of the sea. Wow. The machines were dismantled except for the cutting heads, which were too difficult and expensive to remove. Instead, the cutting heads were left in the seabed, and the holes were filled with concrete. Once the tunnels were joined, the French TBMs drove through the English side, where they were pulled out of the shaft. Tracks, pipes, and wires. Next, workers laid the railroad tracks. Then came the piping and pumping equipment that would carry cold water through the tunnel. The cold water is needed to cool down the heat caused by the friction of the trains. Electricians wired security systems, signaling, and lighting. Workers built crossover tracks between the 2 tunnels. This way, trains could continue running even when one of the tunnels had to be shut down. The Channel Tunnel was finished at the end of 1993. On May 6, 1994, it opened with a ceremony attended by Queen Elizabeth II of Britain and French President François Mitterrand. Cost estimates vary for the project. The highest is $21 billion, making the channel the most expensive civil engineering project in history, which I'm sure China's done something bigger than that now, but who knows. The Chunnel in the 21st century. Since opening, the Channel Tunnel has become a popular way to travel. People drive their cars onto a train at one end of the tunnel, then sit in the car while the train carries them to the other side. Moving at 100 miles per hour, or 161 kilometers per hour, this takes only 35 minutes, replacing a 90-minute ferry ride. Furthermore, some trains offer passenger service from London to Paris or Brussels. This takes about 3 hours. A high-speed rail link on the English side is currently being extended all the way to London, which I'm sure it is by now. London viewers, let me know. In its first 5 years of operation, 28 million passengers and 12 million tons, or 10.9 metric tons of freight moved through the Channel Tunnel. Or freight. Which one do you guys say? It's like either or in America. To many Europeans and tourists, it is a fantastic new transportation system. To engineers, it's a marvel. Yeah, unless you're sitting in it for 4 hours. No, I'm just kidding. It was fine. It wasn't their fault. But that is it for tonight. Thank you so much for watching. I hope that you found this video to be relaxing and educational, and I hope that you have a good